My name is Rodrigo Obando. I'm with Columbus State University. I'm in the Thesis School of Computer Science. And the name of my talk is Mining and Cataloging the Computational Universe of Cellular Automata, a Prospector's Guide. This whole title was not really in there. The last part, they said it was too long. So uh, it's just the Mining and Cataloging the Computational Universe of Cellular Automata. All right, so let's go ahead. I have a lot of things to go through, but hopefully it will give me enough time to go through the last part. All right, so one-dimensional automata, cellular automata. The rules are defined by k number of values, and R is on the as the range of neighboring cells that are in the use. As an example, the ECA is k equal to 2, R equal to 1. And for that, we are able to find, a particular rule that is represented in a rule spaces, where R is equal, is greater than 1, which implies there are many rules that behave the same way. So if you find a rule in a particular place, then you can find it in higher ranges. It will be exactly the same. And of course, it will be represented by a different number. So I'm gonna go through a process here where I show a way to sort of uniform that. And that was the abstract. And so in the introduction, so traditionally, we may define the rules for one-dimensional cellular automata and for the other ones as well, but we define them or declare them atomically. That means that they are self-contained and indivisible. We don't divide them. Now, we define them for a number of values k and for a range r. We use integers to identify them, but these integers depend on a particular value of k and r. So we also know that a given rule for a value k and r can be expressed at a larger value of k. Unfortunately, the integers that identify the rule are different. For instance, rule 110 in the elementary cellular automata is your r equal to 1 is, it is the same as that long number, which is 1,023,163,644, and the rule space defined by r equal to 2. In fact, that same rule is number 28,270 in the rule space defined by r equal to 3/2. So even though they are representing really the same rule, of the integers used to identify them are different. So, you see one, but you cannot really see, oh, that's the rule 10 or 110. That's a big number. It's in another space. So anyway, there have been many ways to parametrize the rules. I'm not going to go into a lot of detail into this because this is really sort of old. For instance, one of those knowns, it was Langton's lambda. A long time ago. This particular parameter, it proved to be useful, but it does not give a good measure of the activity and the evolution of the rule, etc. And I believe even Langton himself said that it didn't turn out to be like he really wanted it to be. So I actually parameterized this. I published a paper, Partitioning of Cellular Automata Rule Spaces. I did this in complex systems back in 2015, and I work a little bit on that and having a way to splitting the different rules into primitives. And the way that this things I'm just going to briefly explain. These primitives, there are a portion of the rules that affect the output depending on the state of a cell or the central cell that is being evaluated. So these are primitives, and these are the colors of the rule. For instance, this is the rule plot for a similar cellular automaton 30, and as you can see here, you have the you have the input, the two neighbors, and then the central cell. And as you can see, the central cell, for instance, that I call primitive 0, is the subset where the central cell is 0. So this one, and this one are actually primitive 0. And the ones that have central cell 1, which are these 4, that's primitive 1. If we were to do this in more colors, of course, there will be more primitives. So this is the way that I designed or defined the primitive 0 and primitive 1. So for instance, rule 204, in that one is the identity rule, has no output changes ever. That means that in this case, the primitive 0, is its own, it doesn't change. And for primitive 1, the 1 doesn't change. The same thing with 51, which is the complement rule. In this case, this actually completely changes. And every one that is in 0, it flips to 1. And every one that is in 1, it flips to 0. That's the complement. And of course, we have 254 other rules besides those. All right, so I divided this. If you're interested in see exactly how that works, I would recommend you reading the paper in complex systems. So looking back, back in 2004, I presented a preliminary view of this, this thing, this rule space, where I ordered. These are the primitives, by the way. These are the different primitives, and these are the primitives for piece of 1. So the combination of these two, and I do have a function, functions that actually combine them so that they create all the rules in between. Order or put the rules in such a way that you could identify. For instance, these are large class 2, this over here is all class 3, all this on this side is class 1, etc. So to me, it was actually very interesting. The problem was that, it seemed arbitrary. It was not arbitrary, but it seemed arbitrary. So can we normalize this? Can we actually do something with this in such a way that it will be, a little bit more useful and not just for ECA? So many people thought that the particular orders, have a reason to be, that we could order in a different way and the distribution would change. And it was right. So we needed to find a consistent order that will work for all values of R. And so we decided to use the primitives and order the rules starting at R equal to 0, something that actually not until recently had not done. We always talk about the ECA as the first rule space, that actually shows interesting things, such as Rule 30 and Rule 110, and all the different rules on that aspect. So we actually, I particularly never really looked below that one because I said, yeah, it's not going to be interesting. But then when I found myself doing this particular, dealing with this particular problem, I said, how about if we go back and look at the beginning, see how they unfold? Maybe I will find a particular order in which, that will be consistent throughout all the different rule spaces. So I did that, and, very, very simple rule space when R equal to 0. R equal to 0 means that in the consideration for the evolution, neither of the neighbors of the central cell is considered for this. So we only have 4 rules. The 0 rule, which is the constant 0. We have the 1 rule, which is the constant 1. So regardless of what the cell is, it's always going to be 1. This one, regardless of what the cell is always going to be 0. And down here, we have a sub naught, or a sub 0. This a sub 0 means that whatever is in the cell is what are going to be the output. So it's the identity. A sub 0 here by itself is just the identity. Whatever input you have is going to be reproduced for the next evolution. And then we have in this last one, which is a sub 0 complement. We, in fact, whatever 0 we have, it becomes 1, and whatever 1 becomes 0, and then for the next step, it also flips again. And as you can see, then it's flipping constantly, 1, and, goes to 1 and it goes to 0, goes to 1, for all the input in here. So these are the 4 rules, not very interesting, not much of activity. In fact, the blue tells me that they are class 1. This one over here is sort of, class 2, you know, in terms of the coloring, because it's, you know, has some changes in there. So not very interesting, but they said, what happens now when I go from this particular space to r equal to half? And now we're going to be using, you know, this is for using cellular automata. I normally use the one on the left. So here we are going to consider, of course, the central cell and the neighbor to the left, you know, which is denoted as a minus 1. And now we see that we have 16 rules. And we have 0 again here, but by the way, it's on the same position as it was before. 1 here is also on the same position, that is the same corner. Then we have a sub 0 on the bottom here, also in the same corner. And then we have a sub 0 complement, also in the one on the right. So we have that actually preserves the position with respect to the one before. But now we have 12 more rules. And this one, of course, they are class 2. But this one over here is class 3. These two, these are the complement. This over here, you see, this is the complement of this one. So these two are complement of each other. And now it becomes a little bit more interesting, of course. And this is for r equal to half. So if I continue the same thing, and by the way that this is happening is that there is a way that I can find which are the primitives that will go into this two in between 0 and a sub naught, and the same thing with this one over here, so that I can generate all the other 12. Again, you know, there's a lot to say about that. All right, so the next one is for rule space equal to r equal to 1. This is the ECA. This is where we find all kinds of interesting behavior. And now what I want you to notice, though, is that 0 is still in the same position. 1 is in the same position. By the way, I changed the notation to numbers because now it is a little bit difficult to put equations for each one of the evolutions. This 151 over here is actually a sub 0 complement, and this one here, 204, is the identity. But now, you know, where we will find, let's take a look at, you know, go back to this one. You see this one here? You know, there will be 4 new rules in between these two, and the 4 new in here and 4 new in here. So this one, if you see the evolution, is 0, 1, 2, 3, 4. That's the one. Oh, excuse me. This one is the one that is in there. 1, 2, 3, 4. That's the other one. It's the same one. 1, 2, 3, 4. So what I discovered with this is that the same rule, regardless of where I actually mapped it, either I did it in, you know, for instance, if I go back to here, this is like a third from 0 to here. If we consider this 0 and this consider 1, this is at a third, this is at 2/3. If I go to the other space, now this one over here is a 1/3, and this one over here is also at 2/3. So it maintains the position, you know, the relative position with respect to the space. And it happens for all the other ones as well. So here's 110. Here is rule 30, just to give you some idea of what things are. This is rule 60, this is 124, and we have the complements, which actually sit right here, 193 and 137. You know, this is as diagonally speaking, they are the complements, etc. So this is how, you know, I started to look. And then I saw that, you know, I could have a set of primitives and then create the next set of primitives, you know, given that I had. So I had these 2 primitives. With those 2 primitives, I could create the primitives that will actually generate these 2, and then I generate these other ones. And now this is the order, and, you know, that I continue. So that means that now I can generate the other primitives so that I can regenerate the next step, which the next step is for r equal to 1/2. So I'm not going to show the evolution of each one of those rules, of course, because the next space is equal to 65,536 rules. So what I did instead is I did a list contour plot, and then what I did is I computed the Wolfram class. You know, I just go through the evolution, and you know, I make an estimate of what class Wolfram class could that be, and then this is the 65,436 are equal to 3/2 space. And now, as you can see, now look in this in general, as you can see, this all blues that you see in here, these are class ones. So it seems like the majority of class ones are sitting on the edges. And then we see all these other ones, which are class 2 and class 3. And there are some areas, there is some, of course, there's symmetry, but there's also some places where this, you know, the class 1 will show up again, you know, at certain intervals. So this is what did, and then I realized that whenever, you know, when I did this for the ECA with this one, that the rules still maintain relative position with respect to this square. So because we had that fixed position, so we find that as we increase the relative position of a given rule at a value of r is the same relative position of that rule for a larger value of r. So once we find a position of a rule, you found the position of that behavior on the rule space, regardless of the value of r, larger than a given value, of course. Using this method, we need to compute the entire set of primitives, you know, so in the proper order, so that then we can position those in the axis and generate the rules. So this becomes really time and memory intensive for large values of r. For instance, for r equal to 5 halves, you know, we would need to compute a primitive, you know, primitive set is 2 to the 32 primitives. And that, you know, becomes now not a nice thing to do. All right, so so the generation of these primitives, you know, we were able to generate all this, you know, from one set to the other in this. It's an interesting way to do it. It actually, it turns out to be a you know, recursive way that you can generate them. So we wanted to, you know, find this, you know, the transformation that we had was really a set transformation. We were transforming the entire set. So I needed an entire set to generate the next set. And that is what became a little bit difficult when you went into the number of primitives like this one, 65,436. If you want to generate the next one, which will be 4 billion, you know, then you now, you know, if you just want to know the position of one rule in this particular space, I will have to generate all this, which is a lot. So we looked into this and we discovered that you know, that there is a transformation that can tell us for a given rule and given the primitives. You know, this is not done without a partition of the primitives, but given the primitives, we can find what is the relative position on this space that that we created. So this transformation turned out to be a permutation of the bits of the rule, which was incredibly convenient. So we also found, of course, the inverse transformation or the reverse permutation. And these two transformations allowed us to then find the position of a rule in the space. And then given a position in the space, we can find the rule that is positioned right there. So this allowed me then to do not having to compute all the primitives. Now I don't have to compute the entire set of primitives so that I can generate this. I can now say, I want this particular rule, and I want to know where it is. You know, so this manipulate over here, which is to me is not finished, but I'm still working on this. I did it. I actually centered it. And right here, this is radius 1. I didn't do anything below that because it's really not that interesting. But here is 110, right? So this is right in the center, 110. And this two-dimensional here that we can move around. I'm not going to move it because I have it just centered on 110. And this is a random initialization for the rule. The size is 4, which is 4 to the right, 4 to the left, and 4 up and 4 down. And then this is R1. So this over here is rule 110. So according to what I have now, I can go in between spaces. You know, I can then take this rule. This is my center rule right now. And then I go to 3 halves. And let me see, am I computing this? Hopefully I am. Let's see, let me go down on this, 3. So I'm not sure if this is computing. Oh, yeah, it is computing. Good, good, good. I just was not patient enough. I think the fact that I'm broadcasting is actually slowing down my computer to use with Mathematica. But this one over here, this is 28,270, which is the same rule, right? Now we zoomed in because of the change in the 3. You know, because, you know, this was centered at 110. This is 110, but now represented in 3 halves rule space. And now if I go to 2, so I'm going now to the next, you know, to radius or range 2. So I'm considering 2, I'm considering 2 cells, 2 on the left and 2 on the right. And this is it. This is now rule 10, but placed on radius equal to 2. So now I can do, as I said, is now with this convenient transformation, I can just say, okay, now I want you to give me everything but at 5 halves, which is 2.5 radius. And let's let it compute here a little bit. And there you go. Now this is a lot closer, and of course the number, but this is the same rule. It is exactly the same rule. And I can go to 3, but this is, you will see there's a problem with this one because I think it has to do, you know, I'm using rationals for this. And there is something in some of the math that I'm doing in this particular manipulate that is causing this kind of behavior, which it actually gives me all the rules to be the same. Yeah, there you go. So they're all the same. So I need to work on this. As I said, this is not necessarily finished, and I need to figure out why is this doing this. But what this one allows me to do is to go anywhere. So let's see if I go in here, and then I move around, and this is the last thing I'm going to do. I don't want to take too long before we get to the other things. Okay, so this is, you know, again, 110, but and then I can move it this way. You know, I can go and explore any other place on this. And as I said, once we find one rule, we have a label for it. It's a, you know, k-dimensional, you know, see all this, you see, and also look at the neighbors. All the neighbors, they look similar to each other, etc. So, you know, this is a way of exploring the space. You know, we can look at it. As you saw before, I showed the how the entire, you know, 1.5 radius looks like. But anyway, so with this, we can label the rules in normal space. They are k-dimensional vector. Right now, we're dealing only for 2-dimensional. And for instance, just, you know, things that I've heard about is rule 30, 110, 137. 137 is actually the complement of 110. So here we have, this is the label for rule 30. So now have this, now I can, with this number, I can go into any other space, and I know what the rule, how is the representation of this behavior on that other space. Now this one over here is 110, and this one over here is 137. And as you can see, they are just swapping. If you swap the coordinates, you know, that's what you get the complement. So from these two. If I wanted the complement of this one, all I have to do is swap this, and then I will get the complement. Now, this is the to normal space function, and this is the from normal space function. So from here, if I take the primitives like you see in here, then I can actually get back to 30, 110, and 137. So this turned out to be just, you know, it's a wonderful thing that I was able to do this. I didn't have to compute all the set of primitives, which is stuff consuming. So now I could do all this. All right. So in this case, for instance, I can randomly select a rule. I just did it in the ECA, and then I can basically represent it here. You know, I can then represent the same rule except for this one, because this is, I think is half. Yeah, half, it will not represent it well. But all the other ones, they're all the same. But they are all represented in radius or range 1, 1.5, 2, 2.5, and 3. They're all the same. So this actually tells me exactly where that particular behavior is. All right, so let me see. There is this other one. These are some measures on the rule space, and I know I'm about to be running out of time. But then when I looked at this and I said, okay, so let's take a snapshot of the entire space. So I measured the entropy. This is for radius 3.5, and this is the measure of the entropy throughout the space. And as you can see here, the dark parts is lower entropy, and the yellow is higher entropy, etc. This over here, the Wolfram classes. I'm not identifying class 4, but I'm identifying 1, 2, and 3. And as you can see, the entropy sort of lines up with the Wolfram classes line up with the entropy. And then one of the things that I was interested in you know, it was Langton's lambda. So I actually mapped Langton's lambda with respect to this normal space. And then I realized that the lower the value in Langton's lambda is actually up here. Whereas in reality, this seems to be favoring to be low right here in terms of the entropy. So when Langton, back in 1986, started exploring the space, he was moving this way. And this is what most of the people have done through the last, I don't know, 30 years. They moved this way. And of course, he discovered, no, it doesn't really give us a good sense of movement within the space. But now we can see why. So according to this, the entropy actually is lower than this area, and it is higher than this way. But in this case, this is lower. So here, yeah, it may look like it is like that, but in reality, it's not. So anyway, what I did also, I took the lambda, and then the lambda, or the derivative with respect to identity, which is the change in terms of the primitives. I'm not going to go into the detail, but that one actually gives you a better sense of navigation within having low class 1s, etc., or low entropy in here with respect to this moving to the right. So this would be the lambda of the derivative with respect to identity will be a better measure to actually manipulate in navigation through these spaces. All right, so let me see. Hopefully this will not die. All right, so in conclusion, you know, because I know I'm out of time. So we found that this transformation helps labeling the rule behaviors in a consistent way across, you know, values of R. Now that I have that particular vector of rationals, I know exactly what that is, where it is. You know, we can explore now the normal space at different levels of magnification. As you saw, I can go inside. I can now identify this, and then I can see neighboring rules according to this to these numbers. You know, I'm also, you know, we're working on transformations for other values of K, which will give us, you know, higher dimensions, of course, or primitives will be higher dimensions, and which is the number of colors that you're using. And then this will allow us to represent all one-dimensional cellular automata in an infinite dimensional cube, you know, like similar to the Hilbert cube. So the initial findings also, you know, I don't have this to show, but it occurred to me that I could look now into this normal space, and I say, let me take a look at the functions. Remember that every single one of the cellular automata rules are functions. You know, they are Boolean functions. So I said, what happens if I take the monotone Boolean functions, which are a particular set of functions, of Boolean functions, and I put it into the normal space. And what I would discover is that actually it looks like a fractal. As we started magnifying inside this particular space, I started to see the monotone Boolean function showing up, and they will show up in a very similar way, you know, self-similar. As you were magnifying, you're going inside, you end up seeing actually the same configuration from above. What is interesting for that is that, for instance, the number of monotone Boolean functions given number of variables has not been really been solved completely on a closed form. We have found only how many we have, up to 8 variables, and that was found in 1990. I think it was Korshinov, and we have not done anything else after that because the problem is big O and factorial, you know, and we used a Craig one using, 200 hours at the time. So if this fractal that I see in this space is actually indeed a fractal that we can predict how it might actually evolve, I don't know. We might be able to find how is it that the number of monotone Boolean functions grow, you know, as the number of variables grow, you know, grows in here. So anyway, this is, as I said, I wish I had a picture. I do have a 3D view of that where you can see how when you find a monotone Boolean function, you know, at the lower number of variables, and as you go down, they are all in the same position. So it is just fascinating to me. So anyway, this is my talk. All this is provided in the files, except that I know that you will be disappointed. All my functions are not all cleaned up, so I did not put that. You know, but you can look at it. You can look at all this the pictures that I have. So let me then conclude this in here, and I will take any questions. Let me see. This is Emmanuel Garcia says, can you estimate the percentage of class 4 rules for each rule space as R grows? No, I have not done that. In fact, the algorithm that I'm using, I work with some other people back in the NKS summer school a long time ago now that I think about it. And we just did that for class 3, you know, class 1, class 2, and class 3. Detecting class 4 is a little bit harder. What I could do, I guess, is perhaps, I think I found that if you go to the class 4 like we did with 110, and then you go into the bigger space, you will see a lot of the neighbors that are also, they seem to be class 4. But still, it will be like, you know, going around there and picking some of those. And if we were to find a reliable algorithm to detect class 4, then we can run it on this, and then we can run it. Now that we have a normalized space, you can pick 110, and then you move on you know, to the sides, going up and down and to the left, and you know that those, you know, neighbors are probably also class 4. And I also found, I didn't show it here, I found interesting things such as a higher definition version of class 110. And when I say a higher definition is that when you look at 110 and then you look at this other one, which is higher definition, it looks like is better defined, So if you were to sort of close your eyes and or maybe pixelize the higher definition one, you actually get the 110. So it seems to me that 110 is really a behavior that is pervasive throughout, and that you actually can find higher definitions of the same behavior. You know, very interesting, but I have not really done too much into that area. So I don't know if you have any other questions about this. You know, if you have any other questions, or maybe may come to you, you should be able to get my email. Send me a message. As I said, I'm still working on this. I'm trying to clean up a lot of my code. I have actually all this code that I used to generate this is in more than one notebook. That I have to run each one of them separate. All right. I don't know if there are any other questions or interest. If not, and then I guess I will stop here. And I really appreciate all of you coming to my talk. Thank you, Daniel. It's nice to see you around. All right.